Okay, welcome back, everybody. So, the very last thing that we're going to cover in the course. So this topic will kind of round out the course. Which, if you're keeping track, according to the notes, we've essentially covered everything. I think we literally missed like 2 sections or something like that. So we have exhausted the notes. We have exhausted the material for the course, which is good. It's always good. And just in time for an extra office hour session too. So this Thursday there will be an office hour session. It'll be the last office hour session of the summer session, and then you will have Friday off to work on your final, which I will post Thursday evening. So that's the plan. The last topic. Discrete dynamical systems, primarily here. The example that we're really going to focus on is predator-prey models. You may have encountered this before. There's a number of places where you could have encountered this in differential equations in a variety of ways. So modeling predator-prey models with a single differential equation, doing it with a system of differential equations. There's a lot of ways in which to talk about this. So what we are going to do, our basic problem here, jumping right into it, is that we have a population of predators and their prey. So we're going to have owls, which will be our predators in this case, and rats, which will be their prey. Now we'll keep track of the number of owls, and we are going to keep track of the number of rats in this system in the thousands. I think that's the idea here. And so let's denote the number of owls after k months using this. So this is I'm doing this so that you don't confuse my zeros that show up here as being repetitions. So this is the number of owls after k months, moths, and let r sub k be the number of rats in the thousands, just to make it maybe more realistic here, after k months. What's the idea here, right? The idea, of course, is that just like how it works in reality when you think of predators and prey, right? The predators need to consume the prey animals in order to survive. They need them as food. The prey, to make this more complicated, the prey could themselves be predators of other things, so this could be a more complicated system, but we're just going to have predator and prey here. So the prey are preyed upon by the predators, but if they are preyed upon, say, too much, eventually, the number of the prey could go to 0, which would have a bad a bad impact on the predator population, since they need the prey to survive. So there's a balance between these two things. You might say, okay, well, if the predators are eating a lot, that's good. That is good in a sense, but they can't eat too much, because if they drive the prey population down to 0, they will eventually starve. So let's give maybe a system that will be like somewhat realistic. I'm going to put it on the next page because I'm going to say a bunch more things, so I want it on a new, fresh page. So I'm going to write down a system here that tracks this. So the system is going to describe the population of owls after k plus 1 months in terms of the population of owls and rats after k months. So This is going to be 0.40 times the number of owls after k months plus 0.5 times the number of rats after k months, and the number of rats after k plus 1 months is going to be equal to minus 0.20 times the number of owls after k months plus 1.2 times the number of rats after k months. This is my system. This, of course, is discrete because this is, I mean, look at it, right? This is a system of equations where I'm saying that if you view each of these time steps being 1 month, right, to increment 1 month, I have this relationship between these two quantities, okay? To see that maybe this makes sense, let's think of the extreme cases. So think of the extremes. What do I mean by that? What would happen if R was, say, 0? So what if there are no rats? No rats means after k months, R sub k is 0, right? The number of rats is 0. If R sub k is 0, then this means that at each time step, what is happening to the owls? There are no rats. Then at each time step, the update is 0.4 times the previous number of owls. Right? So in the k plus first month, this is 0.4 times the previous month's total number of owls. This means that only 40% of the owls survived the month, right? So only 40% of the owls are surviving in this case. That, of course, makes sense because there are no rats for them to eat. So the owls are starving to death. Okay, so a huge chunk of the owls, 60% of the owls, are dying off according to this. Okay, at each step. Okay, what if R sub k is very large? So let's do another extreme. So a huge amount of rats. This is R sub k is large. What's happening here? Well, according to this first equation, if R sub k is large, then this owl population will actually grow, right? It will grow to be larger than it was, right? This implies if it's large enough, grows. So at the update, going from month k to month k plus 1, this population could increase. This means there's so much food, there's an abundance of food, so that the owls are reproducing more than they're dying off, and so we get a gain in population for the owls. Okay. What about if there are no owls? So the number of owls is 0. Then what happens to the rats? Okay. So there are no owls. In the second equation, this is 0, so the rats grow. They're actually going to grow exponentially, right? Their rate of growth is proportional to the current population, which is exactly that's the definition of exponential growth. So they are growing exponentially in this way. That's what you might expect, right? Now, of course, in nature, why this might not always be great is that the land that they inhabit, wherever they live, has a carrying capacity, right? So it cannot support an infinite number of rats. So at some point, there will be too many rats, and whatever food they subsist on will be diminished, so that eventually there may be an overpopulation problem, which might eventually lead to a crash in the population to below the levels that you started with. Right? That's something that we would have to add in separate here, right, to make this more realistic, but this is just giving you a taste of, what sort of things you could bake into your model. Of course, there are owls, so if there were a bunch of owls, so many owls, what would this mean for the rats? Here, if there were enough owls, right, they could cause a decrease in the rat population, which of course would lead to a problem of having very little or no rats, which, then is a problem for the owls. So this is how these things are connected. Okay. Now, intuitively, of course, all that makes sense in terms of thinking about how they're connected, but this is just making sure that this system is describing something that makes sense with our natural intuition for how these things work. Okay. So we're going to keep track of the quantities of these things in a vector. We'll call this vector x sub k. This is going to be our vector that keeps track of the number of owls and rats in thousands. Rats are in thousands, owls are just the number of owls after k months. Okay, so then we could actually rewrite this equation. So look at this equation. There it is. Take it in, admire it, moving on to the next page, so that I can rewrite that equation as follows. I can rewrite it as this vector containing these quantities after k plus 1 months. That is equal to the matrix 0.4, 0.5, minus 0.2, 1.2, times the previous vector. Nope, or just r sub k, sorry. Gonna rewrite this in even better form here. If I call this a, and I notice this is also x sub k, what I have here, x sub k plus 1 is equal to a times x sub k. Right? Now, you're looking at this, and if you just have seen the previous lecture, you notice that at first glance, at least superficially, this thing looks awfully similar to the thing that we just got done describing. But you might say, well, in that case, on the left-hand side, I had a prime here, right? So it's a little bit different, but in some way, it is very similar. And of course, we're going to see that actually the way we go about solving this has a lot of similarities with what we did for the systems of first-order differential equations that we ultimately wrote as a matrix differential equation like this. This is called a linear discrete dynamical system. And that's what it looks like. Now, this equation that we've obtained, right, is very nice. We're keeping track of time now rather than it being a continuous thing, and we talk about a rate, right, with a derivative. Here, these are discrete time steps. That's how we're keeping track here. Let's say, notice that just like in our previous case where this was a differential equation, we would like to have some initial vector, some initial condition that we're going to impose on this, which in our case would be an initial number of owls and rats. So let's say that our x sub 0, which is going to be the initial number of owls, the initial number of rats, let's say that that is 500 owls and 250,000 rats. Okay, So that, rewriting this, I have the equation x sub k plus 1 is a times x sub k with the initial condition x naught is equal to 500 to 50. So that this looks almost identical to the thing that I just talked about how to solve, right? Now, let's see how this would go. If we just kind of do this in a brute force way where we're not trying to do anything too fancy here in terms of solving this, let's see how this goes. So, keeping track of this step by step here, right? What would I do? So firstly, to get from x sub 1, or to get to x sub 1 from x naught, what do I do? This is a times x naught. Right off the bat, you can see, oh wait, this is the same thing. This is iterated matrix multiplication, right? And so this is a times x naught, but a is this matrix 0.4, 0.5, minus 0.2, 1.2, times the vector 500, 250, which is the vector 325, 200. But then x sub 2 is a times x sub 1. So it's this exact same matrix. This will be the last time I write this out. Otherwise, I'm just going to shortcut it. So here the vector that goes in is this previous vector, 325, 200, which gives us 230, 175. In a similar fashion, x3 can be shown to be 179.5, 164. x4 is 153.8, 160.9, and so on in this fashion. So look at what's happening here, right? The owls are decreasing in population, but also, well, so are the rats, right? Will both of them go to 0? I mean, that could happen under some situations. Will this stabilize eventually at some values? Will it bounce back? Both populations grow indefinitely? Any of those things could theoretically happen if we cook the numbers in such a way, but it's not clear what's happening here. Okay, but of course, just like before, right? I'm not going to keep doing this. You notice the pattern. So the pattern is if x1 is a times x naught, keeping everything in terms of x naught, x2 is a of x1, but that's really, of course, a times a of x naught, since x1 is ax naught. So this is a squared times x naught. And similarly, the thing we have been saying since the beginning of the class, the kth step can be obtained by a to the k times x naught. And so again, we see that iterated matrix multiplication yields to us, we really want to understand matrix powers, right? This is a recurring theme in this course, if you like, right? It's clear that, this is like the 5th or 6th time in this course where this is a thing that we've wanted to look at here. And so, what is the solution to my system? It's this. This is the solution. This is the solution to this linear discrete dynamical system. Okay. But this is tricky because, well, a to the k is nasty. Right? This is always the problem. And this problem has always, for us in this course, had the same solution, which is eigenvalues and eigenvectors, right? Or even better, if you're lucky enough, diagonalization, right? So again, we pass to eigenvalues, eigenvectors, and diagonalization. Okay. So, quick example. Powers of a diagonal matrix are easy. Just like a matrix exponential of a diagonal matrix was easy. If your matrix is diagonal, you can quickly, I'm not even going to do this, but you can work it out yourself. The power d to the k is simply 2 to the k, 0, 0, 3 to the k. You just exponentiate those diagonal entries that way. So, of course, extrapolating on this, if your diagonal matrix is, say, the matrix containing all of the eigenvalues for another matrix, then again, this is simply the matrix that I obtain by exponentiating all of those eigenvalues in this way. Okay. Now, just like before for diagonalization, right? If a matrix A is diagonalizable, remember from previous lecture, this means that there exists an invertible matrix P, diagonal matrix D, such that A is equal to PDP inverse. If that is the case, very quickly, you see this means that A to the K is also diagonalizable, and the diagonal matrix in question that it is similar to is D to the K. Okay, so here's an example. Let A be the matrix 1, 1, minus 2, 4. How do I diagonalize this? I find its eigenvalues. Its first eigenvalue is 2. The associated eigenvector is 1, 1. Another eigenvector is 3. Its associated eigenvector, or sorry, its next eigenvalue is 3. Its associated eigenvector is 1 half, 1. This means that the P in question, reading column-wise, is 1, 1, 1 half, 1. The D in question contains the eigenvalues in the proper order, so this would be 2, 0, 0, 3. So that A to the K is P, D to the K, P inverse, which is simply P here is 1, 1 half, 1, 1. D to the K is 2 to the K, 0, 0, 3 to the K, times P inverse, which is, this is a 2 by 2, so we just have a closed form formula for P inverse. This would be 2 minus 1 minus 2, 2. What is this? We multiply this all the way out. This is 2 to the K plus 1 minus 3 to the K. Reading column-wise, this is 2 to the K plus 1 minus 2 times 3 to the K. Next entry, minus 2 to the K plus 3 to the K. Last entry, minus 2 to the K plus 2 times 3 to the K. Okay, this is actually our formula for A to the K. So this means, for instance, what about when K is equal to 4? A to the 4th can be computed directly from this as just plugging this in, this would be 32 minus 81. Here, this would be minus 16 plus 81. Here, this would be 32 minus 2 times 81. And then this would be minus 16 plus 2 times 81, which is the matrix minus 49, 65, minus 130, 146. This is a lot faster than if you were actually doing this, you know, brute force, right? Actually multiplying A times A times A times A. So you can do it that way, and you can confirm that this is the same thing you get, but this is why this works in this way. The numbers 2 and 3 here, of course, were the eigenvalues here, so this isn't surprising. The 2 and 3 are special in the sense that they are the eigenvalues here. Whatever the eigenvalues were would show up in a way like this. So these eigenvalues directly dictate the property that this system has. So going all the way back to days 1 and 2, lectures 1 and 2, when I was talking about this stuff, when I said that the eigenvalues determine the iterated matrix multiplication model, whatever process you're trying to model with iterated matrix multiplication, the matrix powers, how they behave, are entirely determined by the eigenvalues of the matrix. So this is typically when I'm introducing eigenvalues and eigenvectors to students, this is the first thing I start with, because this is kind of the motivation for why even to consider eigenvalues and eigenvectors. So let's go back to our example. All right, so the example that we looked at was x sub k plus 1 is this matrix 0.4, 0.5, minus 0.2, 1.2 times x sub k with an initial vector x naught of 500 and 250. Okay. So we know what the solution is. Our solution just directly is a to the k times that initial vector. Okay. So let's diagonalize this a. So use MATLAB to diagonalize a. Okay. So what are the eigenvalues here? Using MATLAB, you can find that the first eigenvalue is like 1.045. Second eigenvalue is 0.555. So that you have an eigenvalue. One thing that we'll note, I'll go ahead and do this here. I have an eigenvalue that's greater than 1 and an eigenvalue that is less than 1. We'll see why that's important here in a second. What's the associated eigenvector v1? Associated eigenvector v1 is 0.613, 0.790. The associated eigenvector v2 is 0.955 and 0.296. Okay, so that I can diagonalize A using these. So these will be the columns of P. The diagonal matrix D will have lambda 1 to lambda 2 as its entries. So I'm just going to write P like this. It's V1, V2. And then D is going to have these 1.045, 0, 0, 0.555. And then this would be the same matrix inverse. Okay, if you compute a to the k from this using the same thing that we did in our last example, what I get at the end of that process looks nasty, but it's not so bad, and it's certainly better than doing it the other way. So this would be minus 0.316 times 1.045 to the k plus 1.316 times 0.555 to the k. Next entry, reading column wise, so this would be minus 0.408 times 1.045 to the k. Next would be plus 0.408 times 0.555 to the k. The last two entries, this would be 1.021 times 1.045 to the k minus 1.021 times 0.555 to the k. And then this last entry here would be 1.316 times 1.045 to the k minus 0.316 times 0.555 to the k. I just want you to see the form that this takes and how what we did previously allows us to solve for this. So that using this to compute what x to the k, or sorry, x sub k is, so this is a to the k times x naught. This x naught is 500 to 50, recall. So that what I actually get, this last vector, is 96.91 times 1.045 to the k plus 403.1 times 0.55 to the k. And lastly, 125.0 times 1.045 to the k plus 1.25, or sorry, 125 times 0.555 to the k. Okay. So, of course, this vector just tracks the owls and the rats after k months. So the owls after k months are tracked by this slot. The rats in thousands after k months are tracked by this slot. So that we can actually just, so the one thing to notice here is that 0.55 is dominated by this larger eigenvalue. So these two things, these terms are like negligible compared to these. So these are the things that are actually telling you the size of the owls and rats. Okay, so in the long run for large K, this is exactly, these are the quantities that matter. And so for instance, as K goes to infinity, the ratio of, say, rats to owls is approximately, looking at this quantity here, is approximately, these are going to cancel out when you divide by these things. It's 125 divided by 96.91. So this is approximately 125 divided by 96.91, which is like approximately 1.290. This is like our long time proportion of rats to owls. Of course, rats measured in thousands. Okay. If we change this dynamical system ever so slightly, let's change this system just a little bit to the following. 0.4, 0.5, and then minus 0.25, and then 1.2. So we barely changed this. We just changed this entry here, right? Sorry, times x sub k. Okay. So now, what happens when we diagonalize A? So here's our A. The first eigenvalue of A is 0.987, which is less than 1. And the second eigenvalue is 0.613, which is also less than 1. This a to the k we can find is p d to the k p inverse. This d to the k, I'm not going to write out the whole thing. This is p times these eigenvalues, 0.987 to the k, 0.613 to the k, times P inverse. What this is when I take the limit here, as k goes to infinity, I can pass this limit through so that this is P times the limit as k goes to infinity of this matrix. But the limit as k goes to infinity of this matrix, because these eigenvalues are both less than 1, is actually 0 everywhere. And so what I get is that this limit is the 0 matrix, which means my solution, which is a to the k times x0, is actually in the limit here. Maybe I should say the limit here of this thing is this limit as k goes to infinity of this, which is the 0 matrix times my initial vector, which is just this. So in this slightly modified example, crucially, because the eigenvalues were both less than 1, this limiting matrix, a to the k, was the 0 matrix, which led, even, for whatever initial vector I started with, gave me an answer of 0. So this population crashes. Both of these die out. Maybe it's a different species of owl or something, right? And they're just not compatible with this type of rat in terms of there's some kind of overhunting and then population collapse of both of them, right? So they're definitely not stabilizing. These populations are not stabilizing. They're going straight to 0 here. Okay. So that's that. Maybe I wanted to talk about, do I want to do one more thing here? Let's maybe do one more topic, which is recurrence relations. So it is related to what we just discussed, but I think it's worth talking about before we move on. Whenever you talk about recurrence relations, the most canonical example, the thing that gets talked about the most, is the Fibonacci sequence, or the sequence that defines what are called the Fibonacci numbers. What are the Fibonacci numbers? They are numbers that arise by being the sum of the previous two Fibonacci numbers. We start with 0 and 1. So f sub 0 is 0, f sub 1 is 1. Okay. Then, for n greater than or equal to 2, f sub n plus 2 is equal to f sub n plus f sub n plus 1. Another way to do this, since this might seem a little strange, actually, the way that this would technically work for n greater than or equal to 0. Maybe I should rephrase this in a way. Let's make this match with what I wrote here. Have f sub n be f sub n minus 1 plus f sub n minus 2. There we go. So f sub n is the sum of the previous two in the sequence before it. Initializing the sequence with 0 and 1, what does this give us, right? So f sub 0 is 0, f sub 1 is 1, f sub 2 is 0 plus 1, so it's also 1. But now f sub 3 is the sum of the two things before it, so it's 2. And then f sub 4 is the sum of the two things before it, right? 1 plus 2, so it's 3. And then f sub 5 is 3 plus 2, which is 5. Then f sub 6 is 5 plus 3, which is 8. Then f sub 7 is 8 plus 5, which is 13. F sub 8 is 13 plus 8, which is 21. F sub 9 is 21 plus 13, which is 34. So on in this fashion, right? So if we're writing out sequence of Fibonacci numbers like this. This thing that defines the Fibonacci numbers is called a recurrence relation. And it might not be immediately apparent, but these things are related to discrete dynamical systems, and we'll see how. So question, how is this related to discrete dynamical systems? Well, we'll see. First, if I wanted to write out a sequence of the Fibonacci numbers until I just get bored or pass out or whatever, it would be 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, right? 55, 89, 144, 233, 377, 610, 987, and so on. Okay. The question is, since these are getting bigger and bigger and bigger, how fast does this grow? Is this linear, quadratically, some polynomial, exponentially, right? Maybe a way to answer this is to ask the question, well, what is like f sub 100? How would you do that? Well, one way of doing it, of course, would be compute every single Fibonacci number and then say, well, f sub 100, whatever it is, it's f sub 98 plus f sub 99. But that's like a really bad way of doing it, so that's not something I want to do. Because I could ask, you know, what's f sub 1,000? What's f sub 10,000? Right? Like, yeah, maybe doing it this way is not too bad, but these two, that would be a nightmare to have to try to do that. So I would prefer to have a closed formula for f sub k regardless of what k is, so that I don't have to worry about the size of it, right? So what is the idea here? The idea is that to find some f sub k, I don't have sufficient information to determine like the next one. Although if I know a pair of them, if I know two in a row, then I can determine the sequence from there, right? So all I need to know is like two in a row, right? So let's keep track of those two Fibonacci numbers in a row in a vector. This is what I need. And now, instantly, this question of how are these related to discrete dynamical systems, you've probably figured out here. Because now, if I wanted to try to keep track of these using a discrete dynamical system, x sub k plus 1 is the same as f sub k plus 1, f sub k plus 2, which in terms of what these things are, I'm going to keep this as f sub k plus 1. This is equal to, so what is this here? F sub k plus 2, I can use the Fibonacci recurrence relation. All right, going back here. Using the Fibonacci recurrence relation, I can write, this is, I'm not going to do anything to the first entry. This is still f sub k plus 1. Here, f sub k plus 2 is f sub k plus f sub k plus 1. This is just saying that f sub k plus 2 is the sum of the two Fibonacci numbers before it. Rewriting this as a matrix equation, this is 0, 1, 1, 1 times the vector f sub k plus 1. But this vector is just x sub k. So I have a discrete dynamical system, which is x sub k plus 1 times the matrix, or is equal to the matrix 0, 1, 1, 1 times x sub k. And I actually have an initial vector. It's the vector that initializes the Fibonacci sequence. Hey, there it is, 0, 1. And so we have arrived at a discrete dynamical system from a recurrence relation. You can do this with other recurrence relations, not just the Fibonacci sequence. All right. Now, what is the solution to this? So just like our previous analysis of discrete dynamical systems, solution is given by what? Solution is given by this. It's a to the k times that initial vector. Now, to remember, how do I find the characteristic polynomial of a? This is the determinant of a minus lambda I, which is going to be a minus lambda I here. What is this? This is the determinant of the 2 by 2 matrix minus lambda 1, 1, 1 minus lambda, because a, just to remind you, a is the matrix 0, 1, 1, 1. So what is this determinant? This determinant is the quadratic lambda squared minus lambda minus 1. So I'm looking for roots here. Lambda squared minus lambda minus 1 is equal to 0. What does that mean? It means that lambda, using the quadratic formula, lambda is 1 plus or minus the square root of 5 over 2. So this has two eigenvalues, which I will denote as phi and c. The first one is phi, 1 plus square root of 5 over 2. C is 1 minus square root of 5 over 2. These are my two eigenvalues. You already see what's happening here. Maybe you already recognize this is the golden ratio. The corresponding eigenvectors can be found in terms of both of these things. So the eigenvector v sub phi, we'll say, is 1 phi. And the eigenvector v sub c is 1 c. Okay. So diagonalizing A is P D P inverse, where P is the matrix 1, 1 phi c, and D is the matrix phi 0, 0 c. Right? So that P inverse you can find very quickly using the inverse formula for 2 by 2's, and the fact that the determinant of P is equal to minus square root of 5. So P inverse is 1 over root 5 times minus C 1 phi minus 1. Putting all these things together, A is P dP inverse, which is 1, 1 phi c times phi 0, 0 c times 1 over root 5 times minus phi 1 phi, minus c 1 phi minus 1. Multiplying all of this out, actually I don't even need to do that yet. I will look at a to the k. What is a to the k here? So this is the same thing. I'm not going to rewrite that. So it's p. D to the k is phi to the k 0, 0 c to the k p inverse. Ultimately, what do I get here? I get that this is 1 over root 5 times, I get a 2 by 2 matrix here, minus c phi to the k plus phi c to the k. I'm reading column-wise here, so this is minus c phi to the k plus 1 plus phi c to the k plus 1. Next entry, phi to the k minus c to the k. and last entry phi to the k plus 1 minus c to the k plus 1. Okay, so that our solution x sub k, which tracks the Fibonacci pair f sub k plus 1, I find this as a to the k times x naught, which is this thing times our initial vector of 1, 0, or sorry, 0, 1. So that I pick out exactly this column, so that what I get is 1 over root 5 times the column phi to the k minus c to the k, phi to the k plus 1 minus c to the k plus 1. So that the formula that we're actually looking for is this top entry here. So that what is f sub k approximately? Right. Actually, I don't even need to here. F sub k, just directly from this. F sub k is equal to 1 over root 5 times phi to the k minus c to the k. If I actually write out what this is 1 over root 5 times 1 plus square root of 5 over 2 to the k minus 1 minus square root of 5 over 2 to the k. What's amazing is that all the Fibonacci numbers are positive integers. Right? Look at all of them. And because they're defined as just the sum of the previous two things before them, they're all going to be positive integers. So how is this for every value of k a positive integer? Right? That's pretty incredible. It's amazing, right? If you look at an expression like that, you would never think, just looking at it, that this is always an integer. Because, of course, golden ratio, phi, is 1 plus square root of 5 over 2, which is 1.61803398887, and so on. I'm going to stop here. And c is 1 minus root 5 over 2, which actually has a nice characterization as it's like you subtracted 1 and put a minus here. Right? Okay. Okay. So, because this thing is, its absolute value is smaller than 1, this one is larger than 1, this is the one that dominates. And for that reason, looking at this expression, for large k, f sub k is approximately phi to the k over square root of 5. Now, how does this help us? Well, recall that we wanted a quick way of computing like the kth Fibonacci number, right? Because computing like the 10,000th Fibonacci number might be extremely annoying if we're trying to think in brute force terms, where you have to compute all, like, 9,998 of them before, and then add, the last two in that sequence to get the actual answer here. We don't have to do that here, right? So what's an example? Like, what's the 21st Fibonacci number according to this? Well, this is approximately phi to the 21st over square root of 5, which, if you actually compute that out, what is that? That is 10,945.99998. So we have pretty good idea that the 21st Fibonacci number is 10,946, and it is. Okay. So the other thing that this tells us is that this Fibonacci sequence, if I look at the ratio of the k plus first term to the kth term, what I get is that this is approximately, for large k, what is this? This is 1 over root 5, phi to the k plus 1 over 1 over root 5 phi to the k, so that this is phi. What does this say? It says that this is the ratio of the consistent Fibonacci numbers. What this also means is that this limit is phi, which means that this is the asymptotic ratio of the consecutive Fibonacci numbers, and that Fibonacci grows exponentially with phi as its base. So these Fibonacci numbers do in fact grow exponentially, and the base of the exponent is phi. And this is where the golden ratio comes in for the Fibonacci numbers. Now, going all the way back to the very first thing that we started with, this recurrence relation. We took this recurrence relation, we turned it into a discrete dynamical system, and then we proceeded with the exact same approach that we did for this diagonalization bit. This is the same thing ultimately we did with matrix exponentials for solving differential equations, that systems of first order differential equations, that is matrix differential equations. So this gives you another tool to use in a way that ultimately, like, why is this working the same? It's because the underlying linear algebra is working the same. Yes, the thing in question is a discrete object rather than a differential equation, but the way that we were treating it is as if it was a discrete thing anyway, that going to the next time step was iterating through matrix multiplication again. So this is like our last example of how this iterated matrix multiplication business is useful, and I think it's fitting to end the course here. So that is it. That is all of the material. I hope you enjoyed the course. I hope you enjoyed Math 401. Like I said, I'm going to hold office hours on Thursday. After office hours are over, I will post your final exam, maybe an hour or two after office hours end, sometime Thursday evening, and then you'll have roughly a day to finish by Friday night at 11:59, and then that will be it. That will be the course. The course will be over, and you will have completed Math 401. So anyway, that's all, and I hope to see you all around. So I will see you later.